Okay, let's get started. Good morning in Switzerland and good evening in Japan. So welcome to the first EPFL CIS and RIKEN AIP joint seminar series. So my name is Masashi Sugiyama. I'm director of RIKEN AIP Center. And actually RIKEN AIP and EPFL CIS had a memorandum of understanding, I think last year in May. And then after that, actually we decided to have a workshop in summer 2020. But unfortunately, due to COVID-19, we decided to postpone it to this year, this summer. But unfortunately, again, we had to postpone it. So then now it's already more than 1 year. So we had a discussion and we decided to have an online joint seminar to have more communication between two organizations. So this is the first round. So we made a web page like this. So this is the joint seminar series web page. And today, so the first speaker is Professor Volkan Sefer from EPFL. So he's a kind of counterpart of our center and he's the leader of this seminar series. So today he will be talking about optimization challenges in adversarial machine learning. So then after that, so we have more speakers in this month. Okay, next week I will be a speaker. Then after that, on 20th, so Taiji Suzuki from RIKEN will talk about optimization theory. Then October 27th, so Nicolas Flammarion will talk about implicit bias of SCD. So in this October, we try to have 4 talks every week, every Wednesday. But after that, from November, we have a little bit less frequent, but hope we can continue this seminar series for, I don't know, half a year or something like that. Already we have more than 10 speaker candidates, and we will have, I think, quite interesting talks quite frequently. Okay, then so I will finish my opening speech and I pass the microphone to Volkan. So would you start your presentation?
Thank you, Masashi. So a lot of credit goes to Masashi Sensei in this particular case, that he initiated this particular interaction. It's been really unfortunate due to COVID, but ideally, what we would like to do with the seminar series is build up towards some mutual visits between RIKEN researchers and EPFL researchers, which is also funded by the EPFL's CIS Center for Intelligence Systems Center, whose executive director, Jan Kersken, is also with us in this particular presentation. Now, what I would like to do is talk about a very relevant problem in machine learning called adversarial machine learning. And I'd like to acknowledge quite a few sponsors here: ERC, European Union, ARO, ONR, SNF, the Swiss Science Foundation, Swiss Data Science Center, Zeiss, Hassler, and Google AI. So the slides I use today relies on quite a bit of past work. Some of the material can be found in my lectures in mathematics of data. I also posted the slides on Twitter, so if you would like to have copies of them, you can access them. Some of the material I also used for the optimization for machine learning workshop at NeurIPS last year. Our USIPO tutorial, DS3 summer school lectures, and the ISD machine learning physics and mathematics seminar. All right, so what I would like to do in the next 45 minutes is to talk about adversarial machine learning, but what I'm going to do is take a maybe higher perspective and talk about it from a mathematical template that captures quite a few problems. So what we will be doing is literally looking at a single formula, which is minimize with respect to some decision variable x, maximize with respect to some decision variable y, some coupled function phi xy. And this looks like a very simple formula, but it has many important and broad applications beyond machine learning as well. But what I will do in this particular presentation is talk about 3 examples. Adversarial training is one. Then we're going to talk about generative adversarial networks, and as time permits, I'm going to give you some examples from robust reinforcement learning to make some of the ideas a bit more concrete. Now, Let's begin with a bit of a warm-up and set up the notation. So given this particular optimization template, I will talk about, for example, the argument of minimizers or the maximizers, which I will denote as X star, Y star, and the equilibrium or the min-max value will be denoted as phi star. Now, this particular template is interesting because if you think about it, the inner maximization problem implicitly defines a function, meaning this particular optimization for any given X will spit out a value. And I'm going to denote that as f of X. And you can think of this going from here to there. The template is flexible enough to capture many other problems like minimization problems. And in particular for the adversarial training, we're going to work in this direction. And then when we talk about things like generative adversarial networks, we're going to go in this direction because it's going to give us some advantages to work directly with the min-max optimization template. And when we have a minimization problem, the argument of the minimizer is going to be X star, and the optimal objective value will be F star. Now, here is the end user agreement, the Apple fine print in the SQL. So I think that I have a cable issue. In the SQL, I'm going to make some basic assumptions, and we're gonna, so some of the things I'm going to assume is that the constraint sets are going to be convex and has some projection operator, pi x. So when I talk about convergence characterizations, all the iterates of the convergence characterizations will be feasible. We'll talk about things like gradient mappings, which is something like the norm of the gradient, but for constraint problems, which will look at the sequence minus the updated sequence projected onto the constraint set, appropriately scaled. When I talk about L-smooth functions, I mean that they have Lipschitz continuous gradient, which is you look at how fast the gradient changes when you change its input, which will be upper bounded by a constant L. And this partial notation will refer to the generalized subdifferential. And if you see a delta function with a subscript, that will be the indicator function for the given set. All right, now let's begin with the motivation for optimization problems. According to Euler, anything in nature can be written as an optimization problem, but not all optimization problems are interesting. What we're going to talk about is a supervised learning problem from Vapnik's famous paper. So there, in this particular paradigm, we have let's say a generator that gives us some features, data AI. There is some supervisors that looks at these features and gives us maybe labels, classes, or some regression coefficients, or even probabilities BI. And as the learning machine, our job will be to figure out this mapping that the supervisor uses from AI to BI. Now we can talk about a whole function classes in order to do this particular mapping. But in this particular presentation, we will be interested in parametric function mappings in the sense that we will have a function h, which will be parameterized by some vector x that will take in AI, and it will try to approximate BI in some fashion. The way we do this is, at least, for example, given the training data, what we can do is look at the data fidelity, and we capture this with some loss functions, L. So here, loss functions are typically metrics that take in two inputs and satisfy certain properties like non-negativity, symmetry, triangle inequality. And here, what we will do is, given, let's say, n data samples, we're going to try to minimize the loss between our prediction and what the supervisor gives us, BI. And we're going to form the empirical estimate of the quote-unquote statistical risk based on this particular loss. And this will be our optimization problem. And we're going to try to minimize it with respect to the parameters of our function. And there are many loss functions used in machine learning. I give you 3 examples here. One is the logistic loss, typically used in classification problems. Squared loss, typically used in regression problems, and hinge loss, which is also used in classification problems. Now let's talk about an interesting class of functions that have been making a splash over the last decade or so, which are neural networks. A neural network is an interesting construction. What it does is it takes the input, applies an affine mapping, followed by a nonlinearity called the activation function, which is again followed up by another affine mapping. So if you think about this particular affine mapping, so here I'm showing you let's say a single hidden layer neural network. What we can do is take the parameters of these affine mappings, including the biases, stack them into a vector, and this will be our unknown parameters that we optimize this particular deep learning problem. And if you actually really want to make it deep, what you do is you recursively apply the structure. So you put another sigmoid here and then put biases outside and so on and so forth. That way, more layers. It's called a multi-layer neural network. As you add more layers, it becomes deep, and this is called deep learning. Why are we interested in neural networks? Well, it turns out that neural networks are universal approximants. So let's say you are given a hypercube in d dimensions, you can pick up any function, and it turns out that you can approximate this particular function by increasing the width of these hidden layers. So you can have an arbitrary close approximation of any function given sufficient width. But of course, the caveat is that, the width may need to go to like infinity or needs to be exponentially large. But why are we really interested in neural networks is actually the performance that they have been getting in many important applications, such as vision applications. And, around 2017, there were papers that talk about how neural networks achieve superhuman performance. And this was really, let's say, an important moment in machine learning. All right. And of course, one has to be careful. Beyond superhuman means beyond one person's performance on some of these imaging data sets that people use in challenges. And this was Andrei Karpathy, who's, I think, at Tesla, who basically painstakingly went over some of these visual recognition challenges and created a baseline, and noticed that some of these neural networks actually do beat that baseline. Now, given this particular deep learning problem I mentioned, there are many challenges, in particular scalability challenges, because if you have, let's say, an infinitely width neural network to approximate any function, how do you store this neural network? How you compute these parameters? These are really important challenges. What I would like to pay attention to in this particular presentation is something that even if we could have this computational power, storage, and optimize these neural networks, they have an important issue, which is the robustness. And I'm sure maybe I'm preaching to the choir here, but I'll bring your attention to 2 examples. In one, that you can take neural networks and add imperceptible inputs, perturbations to their input, and you can really fool their classification decisions. And I think that if you look at this particular image, no human being would say that this is a rifle, but a neural network does, because it is perturbed by some small pixel-wise perturbations that fool the neural network. Similarly, I think the Tesla engineers show that by putting some sparse perturbations on things like stop signs, you can fool the vision systems in not recognizing the stop sign. Well, again, a human being would not have trouble here recognizing the stop sign. I'm not saying that there does not exist perturbations to human visual system. There are in fact many other perturbations that also work, and similar problems do exist in neural networks that we need to be careful about. Unfortunately, it turns out that these adversarial perturbations are inevitable, and in the high dimensional setting that we really cannot avoid them, if even in this particular simple problem setting. So what I would like to give you is some explanation as to why they're not avoidable, and the intuition in small dimensions, how it does not generalize to high dimensions that we really work with neural networks. So consider the following example. An adversarial imperceptible perturbation, you can think of it as picking some data point in space and adding a bit of, let's say, noise on top of it. So let's take the following example. So let's take this disk. Let's have uniform data on one hemisphere and another class in another hemisphere, cats versus dogs. And let's make the classification boundary in the middle, the equator. This means that if you are interested in just perturbing the data points with an epsilon, so what you can do is take an epsilon strip here. This means that you can take the data points within the strip and perturb them in order to change the classification decision, which is defined by the neural network here. All right. Now, how much of the data points can be perturbed in this particular case? Well, you can say, okay, so the area here, the ratio of this area to the whole disk gives us an idea about the, let's say, the percentage of the data points that we can perturb to fool the classification. And in this particular two-dimensional example, it is actually seems negligible. So this particular area as compared to the area of the whole disk is negligible. This intuition is completely turned upside down in high dimensions, in the sense that if you look at d-dimensional spheres and take an epsilon slice, an epsilon disk in the sphere, it turns out that in high dimensions, most of the volume basically lives in this disk, meaning that if the data is uniformly distributed, you can perturb almost all of the data points with an epsilon so that the classification decision changes. And this is actually called the blessing of dimensionality, concentration of measure, which normally the mathematicians, the machine learners use for their advantage. And in fact, unfortunately, this can be used against us in this particular case. And while one might say that this is a pathological example, it's not, unless the data is somehow non-uniformly distributed. This particular decision boundary of the equator is actually the best we can hope to do in terms of the classifier. Any other decision boundary, like a yin-yang boundary, would make things even worse for us. All right. Now, these difficulties never are a barrier for machine learners to propose solutions to make things more robust. And what I would like to do is tell you a little bit about the adversarial training procedure, or the mathematical formulation in what we can use in order to be a bit more robust against such perturbations. So what I'm going to do is give you a mathematical, basic mathematical problem for adversarial training. In this particular case, in the regular deep learning problem, what we're interested in is minimizing just this loss. But what we will do now is we're going to try to minimize the loss when we know that an adversary can perturb the inputs. So without the adversary perturbing the inputs, we have the usual deep learning problem. But in this particular case, what we're going to do is we're going to be aware in optimization that somebody is trying to perturb the input. And we're going to give them a bit of a budget so that the perturbations live in some ball. In the case of the turtle, it's the L infinity ball with respect to the pixel inputs, so some epsilon perturbations. And in the case of the stop sign example, that would be the L1 ball. And as you can see, that this particular problem, with a bit of massaging, will fit into this particular template that I mentioned earlier, this minimax template. All right, so what can we do? One thing you notice is that this minimax template, in fact, is the second problem that I mentioned when I introduced the minimax template. This is a minimization again over some finite sum of fi's, where individually each fi is this particular maximization problem. So these functions are given to us implicitly. And for each of these functions, you have a deterministic problem in the sense that you're given a data sample, and the adversary, knowing the data sample and your architecture, tries to maximize the loss. All right. So what can we do in this particular case is the question. Now, here are the caveats, and there are many, right? In the loss functions that I was mentioning, oftentimes these losses are differentiable, the models are differentiable. The issue here is that this particular loss function in the end is with the functions that we're interested in, such as neural networks with ReLU activations, with max pooling in between. They're not they're not continuously differentiable, but we're going to sweep this under the carpet for the time being. Okay. So if you were thinking about just basic optimization, one thing we can do is gradient descent. But how do we get the gradient of these functions is a key question. Now, there are many subtleties involved here, and there's like a whole lecture of material, which I will choose to skip for in the sake of time. There are certain things you can use in order to get maybe a descent direction, or a subgradient, or a gradient. But the way you do that is you solve this inner problem to optimality, and then using the optimal solution, you can in fact estimate a gradient or subgradient or a descent direction. In this case, the problem boils down to the following one. We are trying to minimize some function that is given in this finite sum form with several data points. And our objective becomes finding an optimal solution so that the gradient is minimized, meaning we find a stationary point. If the problem was convex, stationary points imply global optimality. But if the problem is non-convex, oftentimes this is the best we can hope to do. In this case, what gradient descent does is it picks up a step size, uses the full gradient of the objective, and then it starts iterating. And when the objective is smooth, the step size can even be constant. But because of the amount of data we have, or the size of the neural networks, we need just, we have problems where computing the gradient is even just extremely prohibitive or expensive, because it basically depends on the amount of data. And if you want to make our optimization a bit independent of the data, more scalable, one thing we can do is use something like the stochastic gradient descent. And in the simplest form, what the stochastic gradient descent does is, as opposed to using the full gradients, it somehow gets a stochastic estimate of these gradients that are unbiased estimates of the gradient with some finite variance. And we can hope to make progress with this particular scheme. Right? So in the finite sum case, what it would do is pick up one of the data points, gets a gradient of this, which would be a stochastic estimate of the full gradient, and then iterate. And in the sequel, we're going to mostly focus on the stochastic gradient descent due to its scalability. And it turns out that it has very interesting generalization properties, as well as implicit regularization properties. So just to set up some additional understanding, with the stochastic gradient descent, what you can do is get other stochastic estimates of the gradient. We can do this by taking batches of data and working with batches of these data. So that would be the mini batch stochastic gradient descent. You would get a stochastic gradient estimate again, and then iterate accordingly. Now, I will talk about also perturbed stochastic gradient descent, because it turns out that the many problems we are interested in are non-convex, meaning that they can have local minimas. And it turns out that stochastic perturbations help you avoid, I mean, this is kind of like the conventional wisdom that if you perturb your gradients, then you can maybe escape these flat regions and go towards local minima. We're going to make this notion a bit more precise in the sequel. But the perturbed stochastic gradient descent, what it does is even if you have a mini batch stochastic gradient, you add a bit of noise and then you work with this particular estimate. So in essence, if you had a stochastic estimate of the gradient with some variance, this adds a bit more variance, but you can still keep the deterministic gradient and add still a bit of noise to it. Within the scheme, if you change the scaling on which you put onto the noise, especially if you scale it with the square root of the step size, this particular thing is known as the stochastic gradient Langevin dynamics. Now, we typically use this for sampling problems, and many people still use it for optimization, which by itself is also interesting. So when I talk about, for example, later on in the reinforcement learning part, when I talk about Langevin dynamics, I precisely mean this particular scheme with this particular scaling on the noise. All right, so let's try to answer some basic questions about this particular scheme. So, I mean, the key question is whether or not the stochastic gradient descent converge with probability 1, whether or not the stochastic gradient descent avoids non-minimum points with probability 1, meaning that in optimization, stochastic optimization for non-convex problems, there are things like traps, saddle points, which I will again make precise. This is not where you want to end up. These are the places where you have at least local minimum is where you would like to end up. So avoiding non-minimum points mean that avoiding things like these or these. Now, then the last question is how fast the stochastic gradient descent converge to local minimizers? All right. Now, the critical point description is as follows. I mentioned that our goal is to find an x star such that the gradient of f of x star is 0. This is what we would call as a critical point. Then, depending on the curvature of the loss landscape around the critical point, we can actually quantify whether or not we have a local minimum, a local maximum, or a saddle point. Now, for this, it suffices to look at the Hessian of the loss at the critical point. If all the eigenvalues of the Hessian are greater than 0, you have a local minimum. If they're all less than 0, you have a local maximum. If you have a 0 eigenvalue, then you have a saddle point. You can also have strict saddles. And there are cases where actually we cannot decide by just looking at the eigenvalues of the Hessian. All right. Now, let me summarize what was known. Now, we knew that the SGD converges to the critical points of the function being optimized as number of iterations went to infinity. In particular, we knew, for example, that the gradient descent itself with constant step size will converge to critical points and avoid any saddle point with high probability unless you initialize it at a saddle point. Now, the issues that we know, for example, with SGD, sometimes having constant step size is important for things like overparameterized neural network optimization. We know that SGD normally doesn't converge with constant step size or even the perturbed SGD. And we know that SGD would converge where we would need things like vanishing step sizes if the sequence is bounded. What we've shown is that under some sublevel regularity of the loss landscapes and some bounded moments on the stochastic gradients, we can prove that the sequence of the SGD converges with probability 1. This is our ICML paper with Panayotis Mertikopoulos, with my former postdoc Nadav Halak, who's a faculty at Technion, and my PhD student Ali Kavish. Now, avoiding traps, things like saddle points, we knew that SGD avoids strict saddles. Now, what was known, which was a wrong gay result from Duke University, was that with some probability that is not converging to 1, with some constant step size, perturbed SGD would escape strict saddles after some iterations, which is inversely proportional to the step size. So in this particular case, we know that SGD does not converge with constant step size. And we cannot basically take the probability to 0. And what we've shown is that with assuming that the noise is uniformly exciting, which is something like an isotropic, but it does not have to have the same kind of noise strength in all directions, then with choosing a step size, which is something like 1 over k to the kappa being in this particular region, SGD avoids strict saddles from any initial condition with probability 1. And now, whether or not SGD will remain close to local minima, there exists some results before, again, Ron Gehed and Jason Lee, I should also mention, some results in this particular research vein. We know, again, that we cannot keep the SGD with constant step size for all problems unless they're over-parameterized. And oftentimes, to talk about convergence, if you have a constant step size, you need averaging, but for non-convex problems, this is not a good idea. What we've shown is that using a vanishing step size, in fact, helps. So you can keep a 1 over k, a fast decaying step size, and SGD will still enjoy a 1 over k convergence rate and objective value. And these kind of things actually do help in practice. For example, if you look at ResNet training for image classification, you can pick, for example, a constant step size for SGD so that you explore the landscape quite a bit, and then you can start decreasing the step size. You can drop it really rapidly, which actually is known as the exponential drop in the literature. We haven't been able to prove the precise form, but there you can always find papers in NERVs and ICML and ICLR about this particular concept. What we were able to prove is that if you were to do 1 over k step size decrease for your SGD, then you can converge to a local minimizer quite rapidly, provably. And in fact, it really helps with your generalization as well. So if you look at the generalization accuracy, if you were to not do this particular decrease, you would slowly increase, but doing the decrease really let you converge fast and obtain a good generalization. All right. So just to summarize, if you think about it, gradient descent and stochastic gradient descent, we talked about their convergences, but this particular class of first order methods, or this general class of first order methods, are very interesting in the literature. And there are many known results for it. For example, if the objective is convex, depending on stochastic or deterministic oracles, depending on the smoothness, you can actually have optimal rates of convergence for your stationarity measure. But the problem, again, with the neural networks is the presence of non-convexity. And what we've done is talked about, smooth cases when you have stochastic gradients and so on and so forth, in which case the optimality measure in the unconstrained case is typically the gradient norm squared. In the case of constraints, you need to look at this gradient mapping that I mentioned at the beginning of my presentation. And there are some rates that are known, but the issue is that the real neural network problems with things like Rayleigh activations and max pooling, they're non-convex, they're stochastic, and unfortunately, they're not smooth. In which case, your stationary measure even becomes much more complex, meaning that you don't look at, for example, things like gradient mapping, but you look at distances to the subdifferential sets. And in this case, there are intractability results. Even computing this stationarity measure is known to be NP hard. And Ohad Shamir, for example, has this beautiful presentation on the elephant in the room, which I recommend. But even in these particular cases, it turns out that there are extenuating structural assumptions, things like weak convexity. So I'll just give you a brief idea about what weak convexity means. You may have a function that is non-smooth and non-convex, but we would call this function a weakly convex function with weak convexity parameter rho if the function with a bit of added strong convexity quadratic, if it is convex, then we can start to talk about convergence characterizations within some epsilon region around the optimal solution where that epsilon is somehow strongly tied with this constant rho. And in those cases, We can talk about giving convergence characterizations on the Moreau envelope as defined here, and giving the characterization in the Moreau envelope actually implies near stationarity for these weakly convex objectives. But remember that we're talking about deep learning. SGD is good in theory. Some people do use SGD in practice, but many people do use adaptive methods. So what is interesting in this particular setting is to talk about adaptive methods. The king of all algorithms, Adam, which is, I don't know, close to 70,000 citations now, and it's corrected version AMS grad. Our group has been looking at things like AcceleGrad and UnixGrad that are universal adaptive algorithms in the sense that they, adapt to the structure of the function without actually knowing if it is smooth or non-smooth, and still giving the optimal convergence rates for it. And under the case of things like weak convexity, we were, for example, at this NeRIPS, we have some work that shows that Adam type algorithms with the correct theoretical modifications, they do in fact have convergence rates under the weak convexity setting. So this is a very interesting area, and there are lots of interesting developments, including lower bounds from Yair Carmon at Technion and his collaborators. This is a very interesting area to work in. All right. So what we've talked about so far is these adversarial examples, right? With from this empirical risk minimization perspective. What I want to do now is to talk about another topic, which is density or distribution learning. So this is a fundamental problem in statistics. The idea here is that we have some data points and we have maybe their frequencies, sometimes their probabilities, which is arguably an easier problem. And as the learning machine, our job is to learn a distribution from them, because having a distribution, for example, helps generate new samples, and it helps us quantify things like uncertainty around, for example, if you can quantify the posterior distributions, you can use it within the machine learning pipeline to make further decisions along the way. All right. So generative adversarial networks is one way of achieving this goal. And there are many examples. I think that things like deep fakes are really interesting here, because these, if you learn a distribution of faces conditioned on the pose of a person, then what you can do is take a video segment, do pose tracking on the face with segmentation, and then use such a distribution generator to generate faces where you can replace the person's face with somebody else's. And hence you can do the quote unquote deep fake here, right? Now, this distribution fundamental problem, normally what maybe the last century of research in statistics did was to assume analytical forms. Given a problem, you can put a bunch of mathematicians and smart people on it, and it would take decades to come up with some sort of analytical function that we can parameterize and then try to learn the parameters of this function. But real applications, you have to somewhat deviate a little bit from the theory and have more expressive distributions. And one idea here is to use neural networks in order to parameterize these distributions via what is called as a push-forward measure. Now, what is a push-forward measure? Now, imagine we talk about a simple distribution, that analytical distribution that we already know, something like a Gaussian. So let's say we have a random variable that is distributed with respect to some Gaussian distribution. Let's say we again have a neural network parameterized by parameters X. A push forward of this analytical distribution with a neural network is denoted as this, which basically captures the distribution of the neural network applied to the simple random variable that we generate with respect to our analytical distribution. Now, this will give, this opens the door to more or less computational thinking in capturing very realistic distributions, such as the distribution of real faces, or the distribution of even, like, let's say a computer graphics ambience for a game where you can generate dungeons or cities at massive scale automatically. All right. Now, what do we need to do in order to set up an optimization parameter to learn such a distribution? We need some sort of a loss function in order to, let's say, characterize how well our chosen parameters would do under our predictor in terms of minimizing our distance to the true measure that we're interested in. So for this purpose, what we're going to do is use what is called as a Wasserstein distance. So what we're going to do is minimize Wasserstein distance, or we're going to try to or hope to minimize this Wasserstein distance between the true measure to true distribution and our push forward measure with respect to our parameters. All right. The issue with this problem is that it is not implementable because we do not have access to the true measure. What we do have access are empirical samples. So what do I mean by that? So let's say this is our true measure. We don't have access to this. What we have access to are samples from it. And note that these samples are more frequent where the probability of the true distribution is higher. They're less frequent when the probability goes down, and we don't have samples across the whole, let's say the real line in this particular case. We have some finite n samples. So what we can try to do in this particular case is to minimize the empirical measure, which is basically these samples with respect to our push forward measure, which is parameterized by our neural network parameters. Right? So the empirical measure would be the delta function in the given data locations. Now, one might argue whether or not this is a good idea. In particular, it turns out that theoretically speaking, this is a terrible idea, because if you look at what we would like to minimize with respect to the true measure and our distribution by a simple triangle inequality, you can see that this is upper bounded by what we can optimize, which is this Wasserstein distance between the empirical measure and our push forward measure, and the Wasserstein distance between the empirical measure and the true distribution. It turns out that our estimator is actually terrible, even though it's an upper bound in the worst case, because this particular quantity has a lower bound, which is something like 1 over the number of samples in dth root, where d is the dimension. So if the dimensions are large, then this can be arbitrarily bad, and hence the optimization that we do may not be reasonable. But Linaik Shizat and Francis Ba has been looking at some extenuating circumstances, and I think that Taiji Suzuki at RIKEN has some beautiful work in terms of trying to understand how this particular quantity varies with respect to some certain structural assumptions. But this is what we can do, and we're going to do it, and hopefully the empirical results will justify the means. All right, so what is the Wasserstein's distance, and what's the relevance to this min-max template? Now it turns out that you can actually write down the Wasserstein distance in the dual form. So if you think about it, this is something like the Wasserstein distance is a non-smooth distance metric in the space of probabilities. We know many non-smooth, for example, objectives like L-infinity norm. One thing we can do is write that in the so-called dual form. In this particular case, you can be sure that this particular non-smooth objective, you can put it into the so-called max form. Hence, we're going to go from this minimize f, where f is the Wasserstein, to minimax form using this duality idea. It turns out that thanks to the Kantorovich-Rubinstein characterization, you can write down the Wasserstein distance between two measures as a supremum over a dual function d, which is constrained to be 1 Lipschitz. And these inner products here basically are integrations with respect to the chosen measure. And they turn out to be, so if you would like to compute this particular inner product, which is in the infinite dimensional space, it's an integral. We have these measures over the, let's say, images. And this is in fact an expectation where the images are distributed with respect to some measure mu, and you evaluate this function at that image. Okay, so if you apply this idea to our problem, then given the empirical measure and our push forward characterization, this has a simple form. You take images with respect to, let's say, your empirical samples, and you evaluate the dual variable. And in the literature, this is sometimes known as, well, most of the times known as quote unquote the discriminator. It is nothing but a dual variable. It does not have any real discriminatory capability. What it needs to be is any one Lipschitz function. And in reality, what we do is parameterize this with a neural network, and we define implicitly a neural network distance, which is an integral probability metric. But enough about that. So here you can compute this, and the second term here you can compute with respect to A's that are generated with respect to our empirical measure, and that actually turns out to have an even simpler form, which is here. All right. So what is the Wasserstein generative adversarial network formulation? What it is that, you know, we assume some noise distribution. We are given some target distribution, which is an empirical distribution. In this case, we have some constraints, let's say, for the neural network parameters, and we have some constraints for our dual variable, or the quote-unquote discriminator variable. And these constraints need to be such that somehow after these constraints, our dual function is one Lipschitz, so that we can actually approximate the Wasserstein distance. Now, this particular problem, as you can see, again, can be formulated in this particular min-max form that we begin with. Now, it turns out that we cannot simply solve this in a manner similar to what we were doing with the adversarial training. We need a direct approach. Unfortunately, there are many issues here. When you look at this min-max problem, there are scalability issues, there are mode collapses, catastrophic forgetting, which I will quantify in a little bit. There are lots of heuristics. And what people tend to do is enforce this particular Lipschitz constraint with weight clipping, where the original authors of the paper, Batu's group, even says, which is a terrible idea, but it somehow works. There's gradient penalty so that the function itself is smooth. And there are things like spectral normalization that people use. Okay, so in a manner similar to the SGD characterization, one might want to think about what we can say about this particular minimax formulation. So what I'm going to do is I'm going to briefly give you the results on this, positive and negative, and then we'll try to wrap up the presentation soon. So key questions. In the sequel, I'm going to assume that there are no constraints. Even in the simpler case, you will see that the hardness is pretty tough, right? So the question is, where do algorithms converge and when do algorithms converge? It turns out that there's a buffet of negative results, even in the simple case that you don't have constraints like in Wasserstein again. Even if the function is smooth and differentiable, deciding whether or not a min-max point exists in the non-convex, non-concave couplings is NP hard. And even if it is guaranteed to exist, finding such point is p-path complete. And even computing an approximate fixed point of the projected gradient descent ascent dynamics is p-path complete. So there's just a hard wall we hit. Now, in the case of finding local minima in minimization problems, in the min-max problems, we in fact try to maybe find what is called as a Nash equilibrium, which is a saddle point. So saddle points in minimizations are bad, but saddle points in min-max optimizations are good. And even we can find a local Nash equilibrium or local saddle point. This is a good thing to do. All right, so here's the definition of a local Nash equilibrium, which this ordering holds locally. All right, so if you recall the SGD results, we can talk about convergence to critical points, avoiding traps, and going to the local optimum. Unfortunately, for GANs, we cannot really have these results. It turns out that, we cannot simply apply such a gradient descent in the non-convex concave case. What we need is some direct approach. So what I'm going to do is tell you a class of algorithms. Then I'm going to tell you about a broad characterization of these algorithms. And then I'm going to end with a reinforcement learning example. So hopefully the rest of the presentation will take 5 minutes. There's tons of citations. We're not going to slide 50, so be assured. Okay, so given this particular setting, what we can do is define this gradient operator, which looks at the gradient of the objective with respect to x and takes a negative, and looks at the gradient with respect to y and takes the positive, and stacks them into a vector, right? And we stack our decision variables as z. So one thing we can do is, if you think about the gradient descent approach, which looks at negative gradient updates, you can basically do this operator updates as if it is gradient descent. So if you think about it, if there was no y problem, this particular thing is just simple gradient descent on the objective. With y in it, it is gradient descent ascent algorithm. There are also implicit formulations such as the proximal point, the extra gradient, optimistic gradient descent ascent, and there are also reflected forward backward splitting approaches that you can use. And I'm going to call this class of algorithms as generalized Robbins-Monroe schemes, where you can think about an algorithm that uses this operator or its stochastic estimate in a manner similar to what we were doing with the stochastic gradient descent, where you take the actual operator and have some perturbation. This perturbation might be biased, or sometimes it is unbiased, and it may have bounded moments and often bounded variance. So all the algorithms that I mentioned in the previous slide fit into this generalized Robbins-Monroe scheme where you have the following update. So you can talk about all these algorithms in one shot within this scheme, where as opposed to having the actual gradient, you can think about having biased and stochastic gradient estimates. Okay. Now here's our addition, the dessert section in this buffet of negative results for Minimax. It turns out that for all these algorithms, they always converge to something called internally chain transitive sets. And these internally chain transitive sets, which is a tautological concept, actually include spurious attractors that do not have any equivalent concept in minimization per se, meaning that these attractors are nowhere optimal. They're not, for example, operator norm being 0, but these spurious attractors literally trap algorithms into like infinite loops, and they don't contain any critical points. So in the case of min-max non-convex, non-concave problems, you can run an algorithm, it may never converge, and you would never know why. I think a visualization is in order. So in terms of optimization, just minimization, the attracting internally chain transitive sets only contain things like solutions, right? Critical points. But for Minimax, attracting ICT sets contains solutions and spurious sets. So here you can think about the simple bilinear min-max problems, which is convex concave, for which we know that the algorithms can converge with the appropriate step sizes. But if you just perturb this setting a little bit, you can come up with spurious attractors that trap algorithms into infinite loops. So here you can start, for example, the extra gradient method, and from any of these initializations, as opposed to going to a local minimax point, it will go to this ring and will cycle around this ring. And the situation can be very complicated because there could be more than one spurious attractors and repellents, such that, for example, here's a local Nash equilibrium. If you initialize your algorithm any point here, it will repel it to this spurious attractor. If you initialize it anywhere outside, all of them will again converge to the spurious attractor. So the only way to get to this local Nash equilibrium in the minimax turns out to be just literally initializing it near the minimax, right? So as you can see, this turns out to be a really difficult problem. And unfortunately, adaptive algorithms are not immune to this problem. So you can run your atom, your extra atom, and so on and so forth. They will again be attracted to these spurious attractors and cycle around without you even knowing it. All right. If the problem was non-convex but concave, there are algorithms that give you convergence in this particular case. And of course, if the algorithm was convex concave, then we have lots of algorithms with beautiful convergence characterizations. So the last thing I would like to briefly mention is that it turns out that such non-convex concave problems, you can in fact convert them into convex concave ones so that you can benefit from this convex concave perspective. And for this, as opposed to looking at these Nash equilibriums, what you do is you lift the problem into higher dimensions and look at what is called as a mixed Nash equilibrium. So think about playing rock, paper, scissors. In test time, you shouldn't play a single, for example, output, not just like all the time rock, because your opponent realizes this and will play paper all the time to beat you. You need to learn a distribution, for example, over the discriminators and the generators, and then try to apply this in an actual test time. So what we've done is we managed to come up with a framework to do this via lifting the problem and looking at the mixed Nash equilibrium. And we have a solution via the mirror descent and the Langevin dynamics. And please see the details here, which was also a thesis distinction at EPFL. And what we've done is apply this to a robust reinforcement learning problem. There in reinforcement learning, we try to learn policies to automate several control tasks. And for the deployment of reinforcement learning in real systems, what you need is for them to be robust against perturbations like frictions. If you assume a certain friction and the friction was a bit different, in this case, your system may catastrophically fail. And what we've done is apply this particular lifting idea there. And we've shown, I think that maybe the details at this minute, not that important. What we've shown is that with the robust approach, you not only gain robustness against certain perturbations, such as relative mass differences, but you also improve the standard performance beyond the standard training, which is also a very interesting observation. And what we've seen is that this lifting idea also tends to avoid some of these limit cycles, which is a very interesting thing to understand in the future. All right, so thank you for your attention. I apologize that maybe I went a little bit over time for this first talk. So what I would like to say is that this robust optimization problems in machine learning that includes adversarial training, generative adversarial networks, and robust reinforcement learning is much more difficult than optimization due to the presence of these spurious attractors and limit cycles. And it turns out that there are certain extenuating structures that we can exploit in order to avoid these limit cycles, which is some upcoming work that I would be happy to talk about later. And having these adaptive algorithms that adapt and improve your efficiency in real practical applications is very important and is a very important research topic that is dear to my heart as well. And with that, I will end my talk. And I'll take questions if we can at this point.
Okay, thank you very much, Volkan. So because now it's like 1 hour, so those who have to leave, so you may leave now, but we may continue having questions and answers. So first of all, let me start. So the latter half was a bit too fast and I couldn't really catch up with it. But so in what kind of case do we observe limit cycles, and what was the real solution to this problem? Maybe I missed some part.
So thank you, Masashi, for the question. So limit cycles, I don't know if you've seen any control theory works. limit cycles and these spurious attractors don't exist in minimization. Okay. So if you think about, let's say, a non-convex optimization landscape, so something like this, let's say this is the global minimum, this is where you would like to go, and we talk about algorithms that will avoid local maximum and saddle points. So this is what we've done in the first half of this particular lecture. We said that things like stochastic gradient descent and perturbed stochastic gradient descent can avoid these traps. Right? So in the minimization, you can think of these as traps, and you would like to avoid them. And it turns out that many of these stochastic algorithms do avoid them. It's just in the case of min-max problems, or let's say online learning in games in general, when you end up having objectives that are non-convex, non-concave, only then these spurious attractors appear. And these spurious attractors are somehow connected to each other. You can go from one spurious attractor to another one. And these spurious attractors are attractors in the sense that if you start one of your algorithm nearby and follow the gradient flow, you will enter into the spurious attractor as if it is a critical point in minimization. The difficulty is that they are in fact not critical points. And that is the issue that does not exist in minimization. That is unique to min-max optimization or general multiplayer games. And this is the difficulty. You can run an algorithm like extra gradient, and these are again attractors. They will attract nearby vector fields towards themselves. The moment you get in, you will just hop around in this internally chained transitive set. You'll loop around and you will not be able to escape. And that is the difficulty in min-max optimization. Does this answer your question?
So, okay, ideally, maybe this happens, but what happens in practice? Like we have...
In practice, the algorithms get trapped here.
Even if we have a like finite step size?
Yeah, finite diminishing step size is also, well, sorry. So all the characterizations, the theoretical characterizations we have, we show the range of step sizes that get trapped into these attracting sets. Even constant step size algorithms can get trapped in these internally chained transitive sets, these spurious attractors. It's very unfortunate.
I see.
And you know, this kind of explains why also this GAN training is very difficult, because if you have an algorithm that gets attracted to this, and in fact, people call this catastrophic forgetting. Okay, so if you ever played with a GAN training with a mixture of Gaussians, which is basically a homework in my math of data course, if you're not careful, if you just run gradient descent ascent dynamics, what you will see is this, you know, you will have these generators, the samples will look weird, it will kind of look something else, and then you will go back to the original place that you were at, as if you've forgotten that you were there. So what that means is that somehow you started with your algorithm, you came here, and then you start circling around, and you got back here. And this is what people say as catastrophic forgetting is a problem in GAN training. This is precisely the reason, because you start cycling around. The moment you realize that you have catastrophic forgetting, this means you're trapped in an ICT set, which is a spurious attractor.
I see. So actually, we had two more questions. Can you see the chat window? Actually, three.
Yes.
Can you see the chat window?
Okay, so there are some questions. So the first question is how to interpret so-called robust overfitting in adversarial training theoretically. So there's a lot to unpack here. I'm not sure what you mean by robust overfitting. So I cannot really comment on this particular question. So So overfitting itself is a known concept in the sense that you have a minimization problem and you have some expressive function class. And what you do is you can get the training error down to 0 with your function, but your generalization performance would be very bad. So just to give you maybe an image example, right? So let's say you have these simple dots you're trying to fit. If you were to fit, let's say, a simple linear function, you're fine. Yeah. Overfitting would refer to the case where you fit with something like this. So
actually, there's an additional comment from the same guy, Jinfen. So robust overfitting refers to
that robustness first increase, then decreases in adversarial training. Okay, so the robustness overfitting in this particular case, when you run an algorithm in the original, as you do optimization, you have some robustness, but as you continue doing optimization, it becomes worse. In this particular case, let me tell you the following, okay? So this is like an onion, so there are many layers, and as you unpeel these layers, it makes you cry. So here's the deal. So suppose you have a true model, all right? This is what you would like to estimate. But when we set up an optimization problem, we set up the algorithm to estimate our estimator solution, X star, okay? And obviously, there is some difference between X star and the true parameter, all right? Now, when you run an algorithm, what the algorithm does is you take iterations. It is supposed to take you towards this X star. Okay, so maybe I changed the geometry slightly here. Oh. Just a second. I'll give you the visualization so that this is clear. This is what we're doing, all right? The interesting thing is, remember, what we care about is this distance, the true parameter distance, and not this distance. Because in the end, we stop an algorithm and we care about how well the algorithm does with respect to this. So the robust overfitting in the end may refer to the case that geometrically, as you're doing optimization and you're trying to get close to your estimator, you can actually pass through a point which is better in terms of your robustness. And then you can start to overfit in the sense that you become more faithful to the estimator that you set up, which is farther away from where you were during the optimization. Does this answer your question? Okay. So, okay, fantastic. So this does answer the question. All right, so let's see. One student here, is it useful to learn model predictive control for better understanding robust reinforcement learning? I think we need to really study control theory, because somehow the splash that the neural networks made with division tests, we should not lose the rigor and the power of simple control theory, because many problems, like taking a shuttle to space, are handled by, you know, model predictive control, H infinity control, right? So I think that by rethinking about the model predictive control with these modern representations and the computational thinking is the better way to go for future, if that answers your question. All right, question. Is there a spurious attractor like zero Hamiltonian trajectories of Lyapunov control theory? So this is a very interesting point. What I talked about were the first order methods. There are things where, as you can notice, in a spurious attractor, the gradient field is not zero. Okay, so if you look at these images here, in this particular trajectory, the gradient field is not zero. One thing you can do is the Hamiltonian approach, meaning that as opposed to looking at minimizing an objective, you can try to look for minimizing the gradient of the objective. All right. In this particular case, though, so that one, for example, will avoid this limit cycle because all the points on this particular limit cycle have non-zero gradients. So the Hamiltonian dynamics will avoid that. The issue with that one is that you can actually go to a maximizer in this particular case, which is the complete opposite of where you want to end up with. Because you know that a maximizer also has a critical point where the gradient is zero. And then you can try to do consensus optimization, which is basically some sort of an average between minimizing the gradient and minimizing the objective. And that really opens the Pandora's box in terms of several interesting problems to consider. I hope that answers that question. All right, another one. So if you look from the physics perspective, we have two fields, electromagnetic and the classical mechanical gravity field. Hence, so I think the question says that is understanding the properties of the vector fields important? Certainly. You know, you can basically look at divergence-free vector fields and give characterizations of a class of algorithms and whether or not how they will perform. So very interesting question. Thank you. Okay, another question. Do floating point formats have any effect on these optimization algorithms, since these methods seem to be more sensitive? Now, this is, you know, I don't know, maybe a $1 billion industrial question. So how to do some of these optimization in floating point. So the way I looked into some of these algorithm characterizations, you can actually tolerate quite a bit of bias up to a point. All right. Then the name of the question becomes, can you somehow give feedback and do corrections even on these quantizations? And there are many approaches that go into this direction. And that's a whole separate research vein in the literature with many active people like Dan Alistar at ISD is looking into this. Martin Yagi is looking into this. There are many people. Ryota Tomioka at Microsoft Research was looking into this, so on and so forth. I hope that answers that question. All right. So maybe, one more question. If you have some comment about deepfake and how to mitigate them, there is always some distribution internally added to the sample, zero-day exploit of the current computer. Okay, so deepfakes present an important security and security concern. The idea is that you know in courthouses, maybe the video evidence now is no longer a real video evidence because it could be easily doctored by let's say somebody who's very capable of working with generative adversarial networks. In fact, what was interesting was this Star Wars TV series. The company itself made one version, and some enthusiasts managed to do even a better one using just generative adversarial networks. So you can doctor videos, and I think some of these things are on YouTube. You can find them. I think detecting deep fakes is a difficult problem. There are security. There's security measures that people can take in, such as watermarking the original videos and so on and so forth. But there are cases where you cannot even do that. In that case, it becomes more or less a distribution learning problem. You have some images that you have, which have some distribution px. Then you have some distribution that you get from the data, and what you need to do is figure out if there was a change point. And this is a fundamental problem that are studied really still by a lot of people, even some Georgia Tech, Yao Ji, is looking into this. There are many problems that are looking into this fundamental problem of detecting changes, and this is somehow known as the change point detection. It's a difficult problem by itself, even without deepfakes. So there are some principled approaches. I think they need to be applied to these particular settings. And no, I'm not really completely on this area. I think Turaj Ebrahimi at EPFL has a startup that worries about, for example, figuring out if there is a deepfake or not. So I suggest maybe try to follow that particular thread of research.
There's one more question in the Q&A window. Can you see it?
Is it need to be gradient penalty and Lipschitz continuity in Hilbert space in order to get the optimal solution? So this particular GAN training, I hope that the sequence of thought was clear. If your original intention is to minimize the Wasserstein distance, what you need to do is you need to make sure that this dual function is one Lipschitz. Now, in general, I mentioned here that we cannot enforce this Lipschitzness constraint because it becomes very hard to do. You can maybe do parameterization with polynomials and somehow get an inner approximation of this. But what people tend to do is parameterize it with a neural network and somehow do graduate student descent on that neural network until the results are good enough for the given application. And when you pick a neural network, what you do is you no longer optimize the Wasserstein distance, but what you optimize is a neural network distance, so to say. It's an integral probability metric that is implicitly defined through this expression. All right. In that case, what people do, such as spectral normalization. So spectral normalization tries to keep the spectral norms. And we know that the product of the spectral norms is basically an upper bound for the Lipschitz constant. So I guess, so there it is a proxy for trying to enforce the Lipschitzness of the discriminator. Yeah, gradient penalty is another one. So if you take the dual norm and penalize it, it's as if you're trying to constrain it. Weight clipping is again a proxy for the Lipschitz constant of the discriminator neural network. So these are the ways in which you try to handle these things. I hope that answers your question.
All right, thank you very much. So we had a lot of questions and nice answers. So that discussion was quite fruitful. So ideally, we wanted to have a coffee break and have a random chat with other people, but this is not possible over two countries. But so the purpose of having this seminar series is to really have a collaboration. So not just listening to a lecture and asking questions, but doing research together in the near future is the real purpose. So hopefully that maybe some young guys may ask more questions offline, and maybe yes, you can also propose some ideas to Professor Siva. So he's happy to have more discussion.
Yes.
And also from next week, so we have still many talks, and whenever you have any issues to discuss, maybe you can directly contact the speakers. Then, so hopefully we can have some nice discussion, and really we want to have a real workshop in the next summer. So until then, so we try to do everything, online. So that's the challenge and purpose. Okay, so please join me to thank Volkan for the great talk today. Thank you very much.
Thank you, Masashi. And I would like to take this opportunity to thank you again for initiating this connection between EPFL and RIKEN. And I hope that this will be a very fruitful one. And I really look forward to the build up towards our physical meeting as well.
Yes, and as we had a question in the chat window, we will put the presentation video today, so on the web page. I think in the near future, hopefully within 1 week or so. Then I pasted the URL, so it's the RIKEN page and EPFL CIS-RIKEN AIP joint seminar series. So you should be able to see the video quite soon. Okay, so then that's all for today. Thank you very much for joining, and have a nice day in Switzerland, and have a good evening in Japan. Bye-bye.
Bye-bye. Have a great evening.